Hi, my name is Lijain Turki and I'm going to talk about magnetic resonance imaging, more commonly known simply as MRI. So today we're going to talk about the physics that allows MRIs to work. So we're going to answer the how, and then we're going to go over the structural components of MRIs. Next, we'll go over the uses, the clinical uses of MRIs, and things that can be diagnosed via MRIs. And finally, we'll link everything together in comparing MRIs with X-rays, CTs, and PET scans. So, the first thing we need to discuss is that protons spin. When they spin, they create a magnetic charge. The protons spin at an acute angle around something we call BZ. So, mapping this on a three-plane graph, the z-axis represents BZ, and the angle that the proton precesses is along the x and y axis. So it's precessing or spinning around the z-axis along the x and y planes. So the angle that the protons precess at, or they spin at, is called Bn, and that's this right here. So basically, when this proton is spinning, of course it's spinning around. So in like a little bit, this is going to be over here in this direction, facing up. And what happens here is that the left component and the right component, they're going to cancel out. So when they cancel out, this leads to a lack of something that we call a transverse magnetic wave. But as you can see right now, we're going to say that there's only one proton involved in this situation. There's one proton, and the direction that it's spinning, based on this arrow here, is spinning up. So when it's spinning up and there's no other proton spinning down to cancel it out, to quote unquote cancel it out, now we have what we call a longitudinal magnetic field. So the longitudinal magnetic field we define as BL, and the transverse magnetic field that we said doesn't exist right now because these two cancel out is called BT. So the number of times that Bn precesses around Bz is defined as the Larmor frequency, and this is the number of times that it precesses per second. And so there's a formula for it, for the Larmor frequency, and it's Larmor, so FL equals, this is a gamma symbol, but it represents the gyromagnetic ratio. Gyromagnetic ratio. So it's different in all different materials, but for protons, it's 42.58. And what that number means is just that the proton precesses or spins around BZ 42.58 times per second. So let's just review really quick. So far we have BZ, BN, BT, and BL. BZ we said is the magnetic field directed along the Z plane. With BN, we already said that when a proton spins, that it creates its own magnetic charge. So that's why it's BN, and it's the direction, the angle of the spinning proton. BT we said is the transverse magnetic field that we haven't said exists so far, and it cancels out, but we'll see in other examples where it does exist. And we also talked about the BL, which is the longitudinal magnetic field. So we keep talking about all these protons, but where are they coming from? They're coming from hydrogen atoms. Hydrogen atoms are perfect for MRIs for a few reasons. First of all, they're a single proton. This means that there isn't the possibility or the risk of two protons from a single atom canceling each other out, either in the transverse magnetic field or longitudinal magnetic field, or a few other things. Second of all, it's abundant in the body. It's in both water and in fat. And the body as is made up of 70% water. So right there, we've already got a lot of hydrogen available to measure. They also have something we call a strong magnetic moment, meaning in the magnetic field, they line up along the axis of the MRI. Now, earlier we talked about the spin up of a proton and the direction that it spins in, and we're going to go into a little bit more details to talk about the spinning of the proton either up or down and how that affects the longitudinal magnetic field. When a proton is spinning, it must either be spinning up or down. The amount of protons spinning in either direction determines the magnitude and the direction of the longitudinal magnetic field. If there's an even number of protons with equal parts spinning up and equal parts spinning down, then they cancel out and there would be no BL. Most protons tend to naturally spin up because this is low energy. Spin down is high energy. So to create a BL, as in to not have equal parts spinning up and down, we need something called a radio frequency of the correct frequency and sufficient intensity that, when available and irradiated, will cause something called spin flip in protons, where the spin up protons will spin down. So they're going to go from low energy to high energy, and they're going to stay like this for as long as the radio frequency is available. So not only does the radio frequency cause them to go from low to high energy, but it also makes the protons spin in sync. So when the protons are spinning both in the same direction, as in up or down, this creates the longitudinal magnetic field. But like we said earlier, the left and right components of spinning protons cancel out, meaning that there is no transverse magnetic field. But what the radio frequency does is it creates a transverse magnetic field. And that is by making the protons spin in the same direction at the same time. So they're all on the left at the same time, then they're all on the right at the same time, etc. So this is super important because the transverse magnetic field is the proton-related magnetic field that we measure. BL is very difficult to measure because it lies parallel to the much greater and much more overpowering BZ. Measuring BT is very difficult. It's small, but it can be measured graphically by placing metal coils near the sample. Right here, we're looking at the proton from a bird's eye view. So we're looking at it from the top. If we're just looking at where the protons are aligned, they're the end of their BN, quote unquote, then we can see that they cancel each other out. So if we pause this circle, here it's paused, it's no longer spinning, we can see. So this proton right here lies opposite to this one right here. So they cancel out. The left and right components cancel out. So here and here, these also cancel out. This cancels out with that, and this cancels out with that, meaning there is no longer any transverse magnetic field. So what if a radio frequency pulse was added? Like we said, this causes the protons to spin in sync or in phase. So what would happen is all of these protons would move and start spinning in the same direction. Now, instead of having all of these protons and showing all of them spinning, let's start to symbolize this by talking about the transverse magnetic field. Let's start by symbolizing this with an arrow. Now that we have this arrow, it's pointing in the direction of where the protons are when they're going to be spinning, the direction that they're facing, and we don't need to show the protons anymore because we already know where they are. So how we measure the transverse magnetic field is via a graph and a coil that is nearby. So this radio frequency, thanks to it, it's allowing the protons to be in sync, meaning they're spinning at the same direction, in the same spot, facing the same direction, as well. So that means they don't cancel out and a transverse magnetic field exists. So how this is measured is via this coil. So the arrow, when it points towards the coil, it means that the protons are in that direction and the current is high. But right here, for example, it's far, and this graph is over time, so meaning that this right here, it's low, and then the closer that the arrow gets to the coil, the higher it gets, and then the further it gets, it goes lower. Excuse my drawings. And then it gets further, and then it gets closer. Of course, I'm going a little bit faster than the arrow is spinning, but you get the idea. So for example, right now, when it's right here facing the coil, that's at its highest. It'll be at its peak. Its peak. And that's how we measure the transverse magnetic field via a graph and a coil. So the radio frequency electrical current in the coils is detected and analyzed using high-speed electronic circuitry. So now having all of these magnetic fields is of no use to us if we can't identify the slice where these results are coming from. So we have three different types of magnetic coils to help us do so and find the source. So we have the X magnetic coil, the Y magnetic coils, and the Z magnetic coils. X measures from left to right, Y measures from top to bottom, and Z measures from head to toe. So these three results are counter-referenced with each other to determine where exactly the result is coming from and the slice to create an accurate image. Okay, so how these results are gotten or how they're received. So we have incident radio pulses. And when they're on and off, these both let us know different things. So incident radio pulses have two very important effects. The first is the reduction of BL, which is the longitudinal magnetic field, and two is the production of BT, which is the transverse magnetic field. When the radio pulses are switched off, though, the opposite happens. Spin down protons de-excite back to the spin up state, and the BN begins to lose phase. Remember, that is the decay of BT. And when they're de-exciting and they're going back to the spin up state, that is the recovery BL. Of course, these two events described are completely independent of each other as they're completely different physics phenomena. So in the previous slide, we talked about the recovery and the decay of the transverse and longitudinal magnetic fields. And here's where it becomes important. The time that it takes the longitudinal magnetic field to recover to 67% of what it originally was before the radio pulses, we define as T1 relaxation. Here, there is a transfer of the energy from the protons to the surrounding tissue. So where this energy is coming from is just as it takes energy and it requires energy to go from the low energy state to the high energy state, when it de-excites, it reverses and energy is released. So that tissue being absorbed by the surrounding tissue is what's measured. This takes 0.3 to 2 seconds, and what we gather from this information is about the tissue's ability to exchange thermal energy with its surroundings. So if we look at this graph over here, we can see T1 over here and T1 again over here, and the varying factor is the Tesla. So this is half Tesla and this is 1.5 Teslas. All the units below are in milliseconds. So adipose fat, their T1 in 0.5 Tesla is 210, whereas cerebrospinal fluid, that's 1800, or in the liver, 350. So what this information is telling us, from T1, we can figure out where the tissue or where the slice is coming from, correlating it and counter-referencing it with what we know and the other information that we receive. There's also something called T2 relaxation, and this is the time for BT to reduce to 37% of what it originally was. T2 gives us information about the homogeneity of the surrounding atoms. Liquids have a longer T2 than tissue because it's significantly more homogeneous. So looking at the graph yet again, here's T2. So if we look at, say, the cerebrospinal fluid yet again, it's at 160 milliseconds for T2. And if we look at muscle, it's 45. So this just tells us that cerebrospinal fluid is much more homogeneous than muscle is, meaning that muscle just has a lot more involved with it and just as a part of it compared to cerebrospinal fluid. So now we're looking at the structure of the MRIs. So we have the radio frequency coils, which emits the radio frequency pulses. We have the patient on the patient table. And we have our magnets, because obviously MRIs, magnetic resonance imaging, we need these magnets. And we have the scanners and the gradient coils. The gradient coils are like the X, Y, and Z that we mentioned a few slides ago. So now on to some of the many uses for MRIs. Anything with the brain or spinal cord, because it's much softer tissue and MRIs excel in this area. MRIs are very good for strokes and diagnosing them and detecting them. For finding cancers such as breast cancer, colorectal, prostate, Alzheimer's, because it's in the brain and it measures the activity. Herniated discs in the spinal cord. Abdominal organ diseases such as liver. Soft tissue damage like cartilage, ligament. Carotid artery disease, aneurysms, detecting source of headaches, and dementia. Now on to our final category. We're going to compare the different imaging tools. We're going to compare X-ray, CT, PET, and MRI. So we're going to look at some similarities and differences between all four. X-rays, CT, and PET scans all use ionizing radiation, but MRI uses non-ionizing radiation. X-rays have radiation shielding, so does CT and PET scan, because obviously ionizing radiation, but MRIs have RF shielding, because we use radio frequency pulses. In the X-ray, metal in the patient is okay, but in CT and PET, it's also okay, but it affects the image a little bit. Whereas in MRIs, it's a major health hazard. So the type of image that we receive from all four, in X-rays we get a 2D anatomical image, and in CTs we get a 3D anatomical image, and PET we get a 3D functional, and in the MRI we get a 3D anatomical. X-rays are very fast, they're less than a minute. CTs are also pretty fast, but they're about 5 minutes. And PET scans are pretty slow. They're the slowest of all four of these. They take an hour to uptake and then 30 minutes to complete the scan and get it all done. MRIs are pretty slow. They take 45 minutes, but of course not as slow as PET scans. X-rays are the cheapest of all of them. And then we have CT that's pretty expensive. PET scan is super expensive because of a cyclotron that's used in the instrument. And we have MRIs, which are also very expensive, but they're expensive because of the superconducting magnets. In the PET scan, there's poor resolution, but in MRI, because it's very sensitive to variations in soft tissue, it has high resolution. Thank you so much for listening, and I hope you learned something new today about MRIs. Thank you.